Hello, we're going to be doing this last lecture of the semester on tsunamis. So get ready to take some notes on all these things. I'll be pointing out important things for you to know. This is a really complicated and a fairly large module. So I'm not going to be worried about everything on here, but there's definitely some things that are going to be important. So the first thing I want to do is just open up a little video and let you take a look at this. And this is from the National Geographic on the big tsunami that hit Japan several years ago. So we'll watch this one.
All across northern Japan, they felt it. A violent magnitude 9.0 earthquake on March 11, 2011.
So write that down, 9.0 magnitude
about
earthquake.
80 miles offshore, and tsunami warnings went up immediately. In coastal cities, people knew what to do next. Run to higher ground. It's from these vantage points on hills and in tall buildings that incredible footage was captured. In Kesanuma, people retreated to a high-rise rooftop and could only watch in horror as tsunami waves inundated their city, knocking buildings into rubble and mixing into a kind of tsunami soup filled with vehicles, building parts, and contents. Seawater cascaded over sea walls and into cities. This video shows the water rushing over an 18-foot seawall in the Kamaishi city. The seawall here was the world's deepest and largest, but not enough for the magnitude of the March 11 disaster. It was the largest quake ever known in Japan, and one of the 5 largest recorded in the world.
That's amazing.
More than 28
5 largest in the world that's been recorded.
When 2 tectonic plates push together under the sea, the resulting earthquake sends an enormous burst of energy up through the ocean, displacing enormous quantities of water. With the upward motion, a series of waves expands in all directions. In deep water, these waves travel fast, up to 500 miles an hour, but only reach a height of a few feet. A passing ship might not even notice.
Okay, that's something that you want to make sure you've written down, that in open oceans, the waves may only have an amplitude of a couple of feet. Ships may not even notice it. And we're going to explain this coming up, but you might want to write this down. A tsunami is a shallow water wave, even though it's in very deep waters. So we'll explain what that means coming up. But now watch what happens when it goes on the shore. He's going to make a couple of comments. Make sure you've written them down.
The waves enter shallow waters. Friction with the ocean floor lowers the wave's speed, but raises their height. This video is from a Japan Coast Guard ship confronting a tsunami wave in shallow water on March 11. And a rare view from the air, video of a tsunami wave approaching the shoreline. In Japan, some tsunami waves reach as far as 3 miles inland. Japan may be the most seismologically studied country in the world, and with more than 1,200 high-precision GPS stations, a geophysicist at the University of Alaska used the data to create a visualization of the March 11 quake. The waves of displacement that you see were moving as fast as 5 miles per second. In this
second.
The ripples of tsunami waves are seen moving upstream in the Naka River at Hitachinaka City. New technology left an enormous amount of visual evidence for study in years to come, and can perhaps help us better understand the power of earthquakes and tsunamis and prevent loss of life in the future.
Crazy. Okay, so we'll shut that. We'll start now on the tsunami module, and we're going to go through a little bit of this thing. I'm going to go pretty quickly, so you'll have to start and stop and make sure you've got everything written down that you need to have written down. So we're talking about these things called tsunamis, which are great waves. And here's sort of a historical idea of some of the major ones. And you start looking at how people have died in these historically. This is a huge problem. 30 to 50,000 people in a tsunami. This is a single day event. That's an amazing stuff. We've had plenty in the United States. There's some that affected Chile in 1960. That was a huge earthquake. And then the ground shook for 7 minutes. And then in 1964 in Alaska, this was a really powerful tsunami. So we got to remember that the two most vulnerable states for tsunamis in the United States is going to be Alaska and Hawaii. And you should put that down. The West Coast is not protected, so the West Coast also has a threat. Now, because the threat is located primarily in the West, the Atlantic side, we don't really expect there to be much in the way of tsunamis. So there are no warning centers for tsunamis out there. So I'm going to go to this page. Actually, I need to go here. It's the Tsunami Warning Center. And when I go here, I've got a couple of areas, and they're going to be located in Alaska and in Hawaii. Okay, so when we look at these centers, here's where they're going to be. The Pacific Warning Center, and then you have obviously this is not Hawaii, this is the one that's in Alaska. So this is more responsible for Alaska and down the Pacific coast, whereas this is more out in the Pacific Ocean. I've been to this building. It's kind of crazy. It is sponsored. It is a National Oceanic and Atmospheric Administration building, part of the National Weather Service, but there's no meteorologists who work there. They're all oceanographers or geologists who work at these locations. So we have two, one's in Alaska, one's in Hawaii, and that you need to know. And the East Coast doesn't have any because it's not really going to be vulnerable to tsunamis. At least we hope not. So again, just pictures that you can take a look at. The reason the Pacific is so overwhelmingly more of a threat than in the Atlantic is this area of earthquake or plate tectonics activity known as the Ring of Fire. So these are all based upon plate tectonic theory, T-E-C-T-O-N-I-C, and you probably need to know this. And we're going to be talking about these boundaries of the Earth's plates that move and why the Pacific is more important than what's going on in the Atlantic, which really doesn't have this kind of a threat. We will explain that coming up later. So lots of things about properties here in the tsunami, lots of pictures. But we are going to kind of skip on to the generation now, okay? How do these things come? So first we'll start with the most important thing about a tsunami. A tsunami is generated by a vertical displacement of water. A tsunami is generated by a vertical displacement of water. So here's some videos. We have an object hitting water. I don't know if they're supposed to, here's a video that's supposed to be with this thing. And what happens is you create all these waves that are moving out. And that's basically what a tsunami is just these large waves. Now, when we look at the plates can do some interesting movement where part of the plate goes up. So the vertical displacement is up, and that's going to push the water and create a wave going outward. You could have the opposite effect where you have a plate that shifts down, and that's going to create a wave also as water acts to fill in the void. We can also have plates that move sideways. These are known as transform boundaries. And if I take a look at this, I'm just getting a shifting, and that causes waves to be generated. Now, it looks like these are just small waves, but if you think about an ocean and a mountain moving in an earthquake, now you're talking about enormous amounts of water that are being moved by tsunamis. Whoops, I didn't want to open that. So let me reopen that. And I think I just want to go back. Okay. So the number one cause of tsunamis is going to be earthquakes. Most earthquakes are going to form along tectonic boundaries, so that becomes our dominant feature. However, there's other things that can happen to get water moving vertically. And part of them are going to be slumps or landslides where the ground actually comes into the water. Now, sometimes those landslides are caused by earthquakes. Other times they're just shifting rock. So there's two types of landslides. There's subaerial, which means under the atmosphere or under the air. So you're looking at land that's up here, and then it just collapses into the water, and that creates a big splash. You also have submarine, which means under the water. So we're looking at areas under the ocean that are going to sink into the ocean, rock slides, and that's going to cause the water levels to change. Now, here's a word that I think is kind of interesting that maybe you should know. It's called bathymetry. And bathymetry is measuring the topography under the oceans. So, you know, a lot of times you go, oh, it's the ocean. It's just going to be a flat floor on the bottom. And that's really not true. There are ranges and hills and valleys and former rivers and slides and all sorts of features that exist underwater. And if you have this hillside slumping where it just crashes down, that's a submarine landslide. A lot of times those landslides, whether the subaerial or submarine, are occurring because of an earthquake, but it doesn't have to be. When we go a little bit further, we can also have volcanoes that can trigger tsunamis. Now, volcanoes also a result of plate tectonics most of the time. Not always, but most of the time. Again, in order for a volcano to do something, though, it needs to generate some sort of a landslide because it's the vertical displacement of water. So it says eruptions can generate tsunamis in several ways, two of which are landslides and pyroclastic flows. If you want to get some information, go look up what a pyroclastic flow is, and you will see some amazing video. I think it's one of the scariest things of nature I've ever seen, where hot molten rock and smoke and ash are rushing down a mountain at several hundred miles an hour. Geologists or volcanologists who study volcanoes, if they're going to die, are probably going to die in a pyroclastic flow, where rocks that are in thousands of degrees are overcoming a person at 200 miles an hour. Good thing is you're going to die quick, but it's going to be kind of a scary place to go. Now, you could have a meteorite hitting the ocean. So a meteor is through the atmosphere, and then a meteorite's when it comes down to the surface. And if it hits the ocean, this could be a really big explosion, and it could generate a tsunami. Sometimes it might be something else like an asteroid, big forces that create tsunamis. The movie Deep Impact, I think, had a meteorite or an asteroid that struck the oceans and created this big tsunami that killed hundreds of millions of people, at least in the movie. Now, if a meteorite were to strike the Atlantic and create a tsunami, other than the fact that we know there's a meteorite that's come down, there's not going to be much time. We're sort of at the whim of whether or not this happens. Yucatan Peninsula actually was formed in Mexico because, not the peninsula was formed, but was affected by a meteor that struck there, created these huge craters. Might have been the cause of dinosaurs going extinct with something like this. So if that hits the ocean, which it can do, we're in trouble. It's going to be you think 2020 is a bad year. Just wait till that happens. So here's the Yucatan Peninsula, that part that sticks out of Mexico, if you want to take a look at this. You also have this thing called a meteo tsunami, where drops in air pressure rapidly can create waves where the water moves up. And now you're not talking about a big wave out in the ocean or in the lake, like Lake Michigan, 3 centimeters. But by the time it gets inshore, it might be greater than 4 meters. That's like 10 to 15 feet. Those are really big meteo tsunamis. So, thank goodness for Wikipedia, because I can do meteo tsunami, if I spell that correctly, which I probably don't. And if I look over here and I go, wow, look at meteo tsunamis, a whole area. What's the biggest ones? Here's some big events. Look who had the big meteo tsunami in the U.S. Chicago, June 26, 1954. The wave height was 3 meters. There were 7 fatalities. So the most famous meteo tsunami in the United States hit Chicago. So that could happen again. People walking down by the shore, and a big wave comes up there, knocks everybody into the water, into the rocks. It's pretty bad. So just remember that. I think that's a pretty important fact to put down in your notes, that of all the meteor tsunamis, Chicago ranks among the biggest in the world, and 7 fatalities. Okay, they have that here, but I wanted to make sure you saw that one in a little bit more detail. Let's see, we can look at areas of the East Coast that might get them. They're not usually really big. So question 1, I want you to answer question 1, and then copy and paste that so that we see what that is. And then look at question 2, because those answers are important. I'm not going to go through it now, but I want you to put that in your notes. Submarine landslides can occur without earthquakes, right? That's a true statement, so keep that in mind. We've talked about that. Now, here's the big plates in the world. You can see this big area where the Ring of Fire was. This is a big plate out in the Pacific Plate. And we have a lot of other plates. Near California, the Juan de Fuca Plate, we have the San Andreas Fault in some of these areas. We have big plates. Notice that the Aleutian Islands, which are volcanic, are associated with these plates. And then you have Japan. You have part of the Philippines that have this type of scenario. You've got big plates that come right along South America. This is why the Chilean earthquake was so large. In the Atlantic, plates are going to do something different. Okay, so if you want to take a look, this is going to be important, but you need to remember this sentence. So go ahead and put this into your notes, that oceanic crusts are denser. Continental crusts, the ones where the lands are, that tends to be thinner and less dense, so that goes above. So plates, when they converge, one's got to go up, one's going to go down. So the more dense one's going to go down, and that's going to be the oceanic plate. Okay, so we're going to talk a little bit more about these things. And again, there's going to be 3 types that I need you to know about, 3 types of plate boundaries. Convergent, in other words, plates are going toward each other. Divergent, they're spreading out. And then transform means they move sideways. So those are the 3 types of boundaries that I want you to know about. So make sure you've written them down. Notice in the Atlantic, it's a divergent boundary. And divergent boundary tends to be just lava, well, magma underneath the ground, and then becomes lava on top, goes under the water, and it moves the water, but it's not like super explosive. It doesn't create tsunami waves. So if you have a chance, go look up at the Mariana Trench and tell me what that is. Mariana Trench, not Mariano's, that's a store. This is Mariana. And you'll find that's the deepest part of the ocean. So take a look at what it says. Put that into your notes, okay? But when we have convergent boundaries, that's where all the big earthquakes are. That's going to be primarily. Now, earthquakes, we're not going to talk too much about, but we have the center of where the earthquake occurred. That's called the epicenter. Okay, that epicenter usually is somewhere in the ground. The closer to the surface, the more dangerous it becomes. But the deep earthquakes can still do a lot of damage. You have seismometers that are measuring the strength of earthquakes. And then the scale that you do that you measured on, is called the Richter scale, R-I-C-H-T-E-R. Now there's 2 types of waves. I want you to think about a slinky that goes in and out. It's a compressional wave. That's called a P wave. And then an S wave is like this wave, this type of a wave going up and down. And they move at different speeds. Because they move at different speeds, when I'm at a place, I can experience the compressional waves first, and then the ground just moving like, and I can say, well, if I know how fast those waves move, I know how far away the epicenter was. I have 3 different sites, and I get a nice 3-dimensional, what we call triangulation. You don't need to worry about that. Triangulation of where that earthquake's epicenter is. So we look at the magnitude. Here's the term Richter scale, R-I-C-H-T-E-R. And that just measures the strength. By the way, a Richter scale, what's really important is the numbers go up to 10, I believe. And you can take a look at some of the major earthquakes. When I go from 8 to 9, I have 1 on the Richter scale, but that's 10 times the amount of energy released. So it's an exponential scale. So if we take a look at that Chilean earthquake, one of the largest ever recorded, if not the largest, was a Richter scale of 9.5. That's huge. The Alaska one in 64 was a 9.2. You do start looking at some major earthquakes at about an 8.0. So these are earthquakes that had significant tsunamis. Notice most of them are 8.0. The one in Italy, the one here in Papua New Guinea is 7. And the reason for that is it probably triggered a landslide. So in this case, there was underwater landslides. So that means that you've got a submarine landslide, right? So it says here, generally earthquakes must exceed magnitude 8.0 to generate a tsunami. However, if we have 7.0, that can trigger some tsunamis also. But 8.0 is that answer. So if you look over here, this is what we're talking about for that one. So you should write that down. That's a super important fact. Stronger earthquakes in general produce bigger tsunamis, but that's not always the case. The tsunami earthquake term was coined to designate earthquakes which generate a larger tsunami than their magnitude would indicate. That might be something you should write down. Probably helped you on the quiz, but you can do that again, all right? Now, I want you to see what's going on with this oceanic plate when it meets a continental plate. The continental plate is less dense. It's going to go above. This oceanic plate is going to go down. It's called subduction, S-U-B-D-U-C-T-I-O-N, subduction. And as it goes down into the earth, it gets warmer and warmer. It's under way high pressure. If you think about air pressure as the weight of the air above you, think about the weight of the earth above you. So super high pressure, super high temperatures, it starts to melt. And that melted rock, molten rock, is called magma. Magma. Magma is under the oceans, it's under the ground, it is in the earth, it is molten. It will then try to come up. If it comes up with resistance and it explodes, then you get a volcano, and then you get the magma going on the ground, and that's called lava. Okay, so we're not going to worry about that too much in earthquakes because we want to get to understanding tsunamis, but this is an important hazard that we need to talk about. Okay, so these people with tsunamis knew that there was an earthquake. Now this one here, how do you think the depth affects tsunamis? It says choose the best answer. Well, I'm going to go with shallow earthquakes. Woohoo! Shallow earthquakes tend to produce bigger tsunamis. And the reason is a shallow earthquake tends to displace more water above it when it's under the ocean. So that's kind of important. While deep earthquakes can be large, quakes 100 kilometers or more below the surface rarely generate tsunamis. Okay, so suddenly we get, and here's just some examples of tsunamis, but most of the time they're going to be at a convergent boundary when one plate, the oceanic, more dense plate, gets subducted. Here's the subduction zone. It may create strain and it slips. All of a sudden it kind of gets together and creates that earthquake. And when it slips, a lot of times the rocks are pushed up or the crust is pushed up and you get a tsunami. Okay. Now there's a lot of stuff in here I'm not going to get to, but I do want to talk about this last one that's called a strike-slip fault. This is a transform boundary where they move past each other. Notice if you took 2 blocks and they're trying to move and all of a sudden they shift rapidly, they can create a really big earthquake. But it's not moving water. So strike-slip faults tend not to vertically displace that much water. Now they can, and I will show you what does that, but for the most part, they don't do that much. So what's the most dangerous boundary? Convergent boundary. Least dangerous, divergent. One in the middle is strike-slip. And that can happen with two things. Number one, they can be oblique. And if they're oblique, or the feature they call obliquity, sometimes they move a little bit, as this diagram's trying to show you, is they can upward a little bit, and that's an oblique boundary. So that's when they become problematic. The other one is when you have this big mountain, and the mountain moves sideways, and it pushes the water up. This is called a seamount. C, S-E-A, and then the second word, M-O-U-N-T. Okay, so I want you to answer this question. That'll be good. And I want you to answer question 2 and question 3. Well, question 3 and question 4 you should know. We've just gone through them. But go ahead, put them into your notes because I think these are important that you know them. And then do question 5 and do question 6. So I'd like to see all of those coming in there with what you do. So those questions there, I want you to do summary interaction. We're going to skip past this. I don't really care that much about this stuff, not for this class. Now we want to go to initiation and see what we have here. So again, it's about vertical displacement of water. Here's a couple of pictures that show about it. There's some displacement. Long ruptures are going to be much more aggressive tsunamis. If it's a long rupture length where there's a lot of rock moving, I think that makes sense, right? Here's some graphed tsunami heights. Look at how big some of the tsunami heights are in terms of centimeters. So 240 centimeters is a huge 2.5 meters of water across Indonesia. Longer earthquakes can jiggle more water. Bigger earthquakes, shallow water earthquakes, shallow depth earthquakes can certainly generate more tsunamis. So you can kind of take a look at this. Again, I'm going to kind of go past this quickly because I'm not going to be testing you on it. Although I think it's going to answer some of these questions if you just want to kind of cement in things with you. But I'm going to skip that for now. Because again, this is a really long med-ed module. Now this next one, the propagation, there's where it's going to become a little bit more important because it now deals with the waves on the water. So wave properties, right? We have crests or ridges and troughs, just like we talked about with ridges in the jet stream. So the distance between two crests or between two ridges is called the wavelength. Okay? Now, we have the water height at undisturbed water level, and you create a wave. So wave height is the distance between the crest to the trough. That's the wave height. The amplitude is only half that. So the wave height is like the amplitude, it's just double the amplitude. Okay, and in the oceans, we get waves because air is moving over the water and pushing the water. So you get these things called waves. Now, here's a couple things about waves moving mass versus not moving mass. So what I'm basically saying is this. A wave comes by and some will move up and down. And if you're in the water, in waves, you're going to make little circles. So if you're ever floating at the ocean and you're just kind of hanging out, floating at sea, you're going to go in and out of the shore, up and in and out, and you're going to go up and down as the waves go by. So you're going to make these little oscillations, these circles. You're going to be kind of moving around like this. And that's typical of what we call a deep water wave. The idea of the deep water wave is as you go further down, you will have less impact of the wave. So it's really wavy on the surface. Let's say you're scubaing and you go under the water a little bit, all of a sudden the waves are not so bad. And that's what goes on. So they're called deep water waves because the distance, the depth of the water is much greater than the wavelength. Remember, the wavelength is from trough to trough or peak to peak, or just one complete wave circuit. And this is much smaller than the depth of the water. That's what makes it a deep water wave. That you need to understand. A shallow water wave, and this is kind of the key thing here, is means that the wavelength is much larger than the depth of the ocean. That's why the tsunami is considered a shallow water wave. In the middle of the oceans are really deep, but the wave itself might have a wave of 500 kilometers. That's way bigger. That's why it's called a shallow water wave. And shallow water waves are going to be felt pretty far down. But you wrote this in that little video, and I want to kind of underscore this. So there's things that are happening as that wave comes ashore, and the water gets shallower and shallower. First thing is the waves slow down, which means the waves pile into each other, and that would mean that the wavelength is smaller. So waves slow down, the wavelength smaller. Okay? And that you could look at the wave height or the amplitude. At some point, water starts moving ashore. It's called the surf zone or the swash zone as the water starts moving. And this time, rather than a wave where you're just making these little circles, now mass is going to be transported. Mass transports on land is called a current, even at the oceans. It's moving water, not just going up and down in waves. Like you in the ocean, and if there's no current, you'll just go up and down for a long period of time. But if there's a current, then you're going to be moving. That's why they have the rip current, which we talked about in class. The rip current, if you don't know what that is, go take a look at what rip current is. And there's actually flow that moves people away from shore. And that's where people start panicking and drowning because they try to swim against that. So understand that waves generally move up and down. They just kind of keep it all there. They transport energy. But a shallow water wave, as it comes ashore, starts transporting mass. And that's the big garbage. Okay, so here's, label this. Go ahead and try labeling that. That would be good. Here's all the stuff. Just drop and drag. Maybe take a picture of that, insert that into your notes. And then the other one that I want you to try to figure out is question 5. Go ahead and do question 5. So just questions 1 and question 2 on this section. There's your shallow water wave where those circles go all the way down to the bottom. So tsunamis are shallow water waves. And what's happening is those little circles I talked about, when you get closer to the shore or closer to the surface, they go back and forth. So as they're coming into the swash zone, that's when the water starts moving on shore and you get these incredible amounts of destruction. So I'm going to show you an amazing destruction. So we'll take a look at this one here. So notice that the water is moving and vehicles in the water, look at how many vehicles are moving in that tsunami. So the water is moving ashore. The land is becoming inundated. Crazy amounts of force in that water as everything is getting destroyed. I mean, this is pretty amazing. There's a boat going down the streets. Okay? This is what I mean by particle motion or mass movement. The water's coming on shore. Now, it's kind of cool over here, and I'll show you another version of that last one. I'll let you see that. But you can see something bad's going to happen. Look at the flood of water coming in. And look at the force that it hits bridges with. Houses, entire buildings are being crushed and destroyed by this. An amazing amount of destruction with these things. So a tsunami is inundation with current that comes on and current that goes out. Here comes the water. Look at everybody running away from it. This is pretty scary because some 10,000 people died with this. Not everybody was lucky. Oh yeah, you better move. That was scary. Look at that. The entire buildings are moving. If you're caught in this, you're going to be hit. You're going to drown. You're not going to be able to swim because of the significance of those waves coming ashore. Let me show you another one of what happens when these waves come ashore. So this is a large seawall, And the water is coming, it's just going, as it's coming in, the level of the ocean is going higher. So in about 5 minutes, it starts crashing over this wall. So watch what happens. You'll see the water like a wading pool. It's taller than the walls can hold back. There it comes. Look at it, there's already a vehicle in there. Crazy. Look how much of the land is inundated with strongly moving water. And it just keeps coming up. Again, think of the wave as being 500 kilometers long, so you're not going to get to the crest for a long time as that wave is. It's going to be several minutes. So, crazy amounts of shore of flooding in this scenario. Now, what I'd like you to do is, and I'm going to be checking for this, is go take a look at that, maybe at a video like this, and just give me your opinion. What do you think about that? Have you ever seen a tsunami water wave do stuff like that? I think it's pretty amazing. So the particle motion goes really crazy, and it does a ton of things. Summary questions. I would do this. Go take a look at this and put these answers, question 1 and 2, in your notes, because I think those are important. In fact, go ahead, all 4 of this section would be important to put into your notes. Again, we're going to make a really good section on this. I'm not going to worry about testing you as much as I want to see a really good outline of this one. So here's the Tsunami Warning Center. And now they're going to go a lot about modeling and how we figure out where the waves are going to be. And there's a lot of information that goes into it. Okay, so when these things are happening, they need to say, well, how is it going to be impacting everybody? So like any other hazard, any WAWA, there's watch warnings and advisories. So I'm going to go to this. Here's the picture I want you to have of tsunami alerts. And this is a little bit different than everything else that we've studied so far. A tsunami watch is usually when there's an earthquake that is possibly triggering a tsunami. Now remember, 8.0 runs the risk. It may not, but it runs the risk. 7.0 can be local. So usually we see these strong earthquakes, and the first thing that these tsunami warning centers will do is issue a tsunami watch. Now, if I issue, well, I'm not issuing, but if Storm Prediction Center issues a tornado watch, you have to understand that's a forecast. We're expecting tornadoes later. The difference here is when a tsunami watch is issued, we issue the watch because we don't know what's going to happen. We don't know if there's going to be a tsunami or not. That's why we put out a watch. Once the watch is issued, they do more investigation. We have buoys that go up and down, and we try to figure out if there's a tsunami. We run it through models. And then, if it's going to be a really bad tsunami, bad situation, tsunami warning. So the watch goes to a warning. Now, what if they're like, oh yeah, there's a tsunami, but it's really small. It's only going to be a couple of centimeters. It's going to cause some currents. Maybe if you're walking on the shore, there might be some waves. We're going to put an advisory, a tsunami advisory. Or they may figure out there's no tsunami, and then they cancel it. So the watch goes up as fast as you can, just in case. Once we know, warning, advisory, or no action, and then we just cancel it. And that's how those things work. Okay, so that's important that you know this. Lots of things about waves and tides. Now it gets into a lot of information. This is more from a geological standpoint. I'm not going to worry about those. I'm now going to go to our next section, which is inundation. Now, inundation says, here's some things that are happening. We've already talked about particle motion, and we've seen these things and what they can do, and the waves get really strong. This is an important thing. How do you think they arrive at the shore? I want you to answer this question. It's really important that you look at those answers. Sometimes the wave comes first. The waters just go up. Other times, the waves come in later. So here's the tsunami situation here. And I want you to take a look at this video. It's so cool. Because this is what happens. They're out there in their boat. Here's a little bit later. Look at all the boats are short. All the water has left. And within a very short amount of time, the water starts coming back in. Now, what happens in this scenario is people will often see the water go offshore and they go, wow, look, all the water's gone. And they go look at shells and they're standing out there like they are and what's going on. That is not a good thing. Later that minute, now the water's coming way inland. This is not good. And now you start to get some idea of the level of panic that are going on. So keep in mind, if the water recedes and you're at the ocean, what should you run? Not in a minute, now. Run, get to high ground. So this is in the module, but I wanted to show you one that I have here that's not from a module, because this is amazing. Okay, I want your reaction. Doesn't have to be a paragraph. What's your reaction to watching that happen? How quickly something like that goes on there. You know, I just think this is amazing. So here's a little bit more of that hotel. When you start seeing this.
It's coming in your way. It's coming
So
in.
they're just kind of watching it again. You start seeing this, you need to get to high ground. And people, especially tourists, have no idea what's going on.
They called me out there.
Look at this destruction. Shit, no kidding. Okay, so this is why if you were in class, I would ask, what did you think? I mean, amazing. And people are just kind of like, they have no idea what's about to happen. These things are just incredible. In fact, of all the disasters we talked about, this is one that scares me the most. So what I want you to do now is I want you to go look at 2004 Indonesia tsunami and tell me what the death toll is that you find. The death toll from this event that came right after Christmas. Because it's astounding, right? Especially in the COVID era. Look at what happened with one event. Okay, so the lands are inundated with water, and we've used that word all semester long. So inundation, just crazy stuff. So in addition to that inundation, don't forget all that water that went inshore has to come back. Now, a tsunami may be a series of waves, so you'll have water coming in and out several times. And every time the water changes its direction, it gets worse and worse. Lots of debris, lots of people can get killed in a situation like that. So again, lots of information here. I'm not going to get into any of this stuff, so we can kind of move forward pretty quickly. I mean, this one should make sense to you, but don't forget, you can have a series of waves. This is question number 3, so important. Is it always arriving with water going out to sea? No, sometimes the water leads the way. Okay, so question 3 and question 4, you need to know. And I would put question 5 in there too. So please go ahead and do that. All right. Let's see. I don't need to talk too much about this. We've already talked about what the force looks like. Heavy water moving, crazy streets being ripped apart. That's the effects of inundation. That's the direct impact by something like this. So I'm going to go through this really quickly, skip past all this, and go into long-term effects. And we're almost done here. And long-term effects are talking about changing the soil. You're putting salt water on. You may change the bathymetry of an area. You can get land that subsides or drops. You have salt killing plants, changing crops that are on shore. All of these things are part of the long-term effects. They can destroy trees, and look at the tree lines missing here, all because of a tsunami. So it affects agriculture. We showed you some of that in Japan, just going over the field. And you've got all this salt water that's ruining it. Here's your tsunami sand, and there's the soil underneath it. And that's a lot of sand and crappy land to try to plant into when you need that good soil. So it changes things for long terms. Don't forget, anytime you inundate, whether it's a tsunami or an earthquake, a hurricane, you're talking about lots of impacts to structures, to people, to bad, infected, disease-ridden water, livestock, death in the water, lots of short-term to long-term impacts. And that's really what we're talking about on this one. So that is tsunamis. It's a little bit longer, but this is going to be an important set of notes. It's going to be worth more points than all the other ones except hurricanes. So do a really good job of putting down a good set of notes. Give me your thoughts about the videos you saw, and hopefully you'll be able to do that. But those are the things that I talked about that you need to know. So that's what you'll be tested on. Okay, guys, have a good one.